Hello friends, in this video we will be learning classification of signals depending upon signal properties. Let us begin. In our very first lecture, we have already learned classification of signals, but those classification signals were broadly classifications like continuous time signals, discrete time signals, deterministic signals, random signals. So such basic types we have already seen. But depending upon the individual property of the signal, we have this type of classification. A very first property is based on symmetricity, or based on symmetry we have got three classifications here. First type is called as even signal, second type is called as odd signal, and one more type is there which is called as neither even nor odd signal. So we have three types of classification depending upon the symmetricity of the signal: even signal, odd signal, and neither even nor odd signal. Based on the periodicity of the signal, we have two types, that is periodic signal and non-periodic signal. Sometimes non-periodic signals are also called as aperiodic signal. Depending upon the value of its energy and power, we have again two types of classification: energy signal and power signal. And depending upon the causality of the signal, we again have three types of classification here. First classification is known as causal, second is called as anti-causal signal, and the last type is called as non-causal signal. Now these are classification depending upon the property. In this video we will be focusing on symmetricity property. So we will be learning even signal, odd signal, neither even and nor odd signal. Let us begin with even signal. A signal x of t or x of n. So the definition that I'm giving over here is valid for continuous time signal also, as well as for discrete time signal also. So whether it is x of t or x of n, if it satisfies the following property, then the respective signal is called as an even signal. For continuous time signal, it is written x of minus t equal to x of t. So if x of minus t happens to be x of t again, then the respective x of t is called as even signal. And same as you can see for discrete time signal, exactly similar definition. The only difference is instead of t, we use n for time scaling. So x of minus n, if it happens to be x of n only, then the respective x of n signal is called as even signal. So what we are doing over here, what is meant by x of minus t? You know very well. X of minus t is what we called as time reversal property. So if you take a signal and if you do a time inversion and still if you get the same signal back, then the respective signal is called as an even signal. So this is valid for continuous also and discrete also. So let us see examples of continuous time signals which are called as even signals. So these are few examples which are considered to be even signal. I'll prove over here how they are called as even signals. So we know that x1 of t signal can be considered as even signal if x1 of minus t happens to be x1 of t only. So by property, if x1 of minus t, we get again x1 of t only, then only x1 of t is called as an even signal. So let us plot x1 of minus t. You know very well how to plot x1 of minus t by using a time reversal property. In time reversal property, what we do is whatever present at right hand side we plot it to left hand side, and whatever present at left hand side we plot it to right hand side. And in fact, what we come to know, since lower limit and upper limit, as you can see, it is same and amplitudes on both the sides are exactly same, I'm getting same characteristic as x1 of minus t. So ultimately what I'm getting, a new signal which is x1 of minus t, which is again equal to what, x1 of t only, and Therefore, I can claim that x1 of t is an even signal. So this is an even signal for sure. But let me tell you, from gate point of view, we need to have some shortcuts. I mean, for every signal, it is not possible for us to do the time reversal and then to check whether the given x of t signal is a even signal or not. Only by observation, you should understand the given signal is even signal or not. How to identify it? It's very easy. You have to first of all concentrate on right hand side part of x1 of t. So I'm talking about this part. So whatever present on right hand side, exactly similar thing if present on left hand side also, then the given signal is definitely an even signal. I repeat my statement. You have to observe the right hand side part of the given x of t signal, and if it is exactly same as left hand side, then it is always called as the even signal. Because in time reversal, this is what we do. We copy left hand side to right hand side and right hand side to left hand side. If both the parts were equal, then even after time reversal, it comes out to be the same signal again, and definitely that signal is called as an even signal. Second example, we can see x2 of t. I'm sure you know what type of signal it is. It is what we called as a DC signal. So what you see, whatever present at right hand side, similar characteristic is present at left hand side. So definitely even x2 of t is considered to be an even signal. So this is also an even signal only, of course. So let us apply the same technique at x3 of t. In fact, by observation, one should understand this is nothing but a cos t characteristic. It is a cos t characteristic, right? It is a cosine signal, in fact. So if you see the cosine signal, whatever present at right hand side here, similar thing is present at left hand side. Therefore, this is 100% an even signal. In fact, you should know that cos of minus theta is cos theta. Is that right? So this is quite analogous to this property x of minus t. If happens to be x of t, then the given signal is said to be an even signal. So I'm sure now by observation you can identify whether the given x of t is an even signal or not. Let us see an example of discrete time signal which is considered to be an even signal. Again, we have to use the same technique. What that same technique is? What I have told you, whatever present at right hand side, if present at left hand side also, then I can say it is an even signal. So you have to check symmetricity this way. Exclude this part equal to 0. I mean to say n equal to 0 here. If this same 3 is present here, if same 2 is present here, and same 1 is present here, so with this symmetry, I can easily say this is the discrete time even signal. So I'm sure now you have understood what is meant by discrete time even signal. So let us assume if we have 1, 2, 3, 0, 1, 2, 3. What do you think? Is that a even signal? Of course, it is not even signal. You cannot say this is 1, 2, 3 and this is also 1, 2, 3. No, not that way. This 1 should get mapped with this. So this is not getting mapped. This 2 is mapping, yes, but this 3 is not again equal to 1. So definitely this is not a even signal. Let us go and understand what is meant by odd signal now. Odd signal definition is given here. A signal x of t or x of n satisfies if following property, then it is called as the odd signal. So let us see, for continuous time signal, what is the property? If x of minus t is equal to minus of x of t, I can rewrite this. I mean, what I'm doing, I'm shifting this negative sign here. So I can write minus of x of minus t is equal to x of t. So when I'm the same thing, then the given x of t signal is said to be an odd signal. Am I right? Similarly, x of minus n is equal to minus of x of n. I'm shifting this negative sign here. So I can rewrite this property as minus of x of minus n is equal to x of n. So what we need to do is, see, in step number 1, I'll do time reversal. Is that right? If I'm talking about continuous time signal, I'll get x of minus t. And let's say if I'm talking about discrete time signal, I'll get x of minus n. Is that right? So first step I have done is time reversal. Step number 2. In step number 2, what we do is we multiply the given signal with -1. That is what we call as reversing the amplitude or reversal of amplitude. So if I do reversal of amplitude, so I'm doing reversal of amplitude. So I'll get minus of x of minus t. In case of discrete signal, I'll get minus of x of minus x. Now after doing so, if you get same signal as x of t, which is original signal before modifying, and here if you get same signal as that of x of n, then the given x of t or given x of n is said to be an odd signal. So once again, first step you have to do time reversal. Second step you have to do amplitude reversal, and even after doing these two operations, if you get same signal back, then the given signal is said to be odd signal, and this is applicable for continuous time signal also and for discrete time signal also. Let us see some examples. First example, you can observe x1 of t. One should understand looking at the signal that this is a signum function. So x1 of t is actually signum of, it is a signum function. Now as I said, I have to do two things. First step, we have to do time reversal. So to do time reversal, I'll do it x1 of minus t. And I'm sure you remember how do we do time reversal. What we do? We shift right hand side part characteristic to left hand side and left hand side part characteristic to right hand side. So what will happen? You will have now plus 1 here and you will have minus 1 here. Is that right? So this is step number 1, that is what we call as time reversal. After that, we do amplitude reversal. Amplitude reversal means multiplying the given signal with -1. So what I'm doing, I'm now going to plot minus of x1 of minus t. I'm sure you remember how do we do that. Positive amplitude becomes negative amplitude. Negative amplitude becomes positive amplitude. So I'm talking about left hand side part. In left hand side part, it is plus 1. This is plus 1. This will become -1. And at right hand side, we have -1. It will become plus 1. And surprisingly, you know what I'm getting is x1 of t only. So here I'm coming to the conclusion, minus of x1 of minus t is equal to x1 of t. This is the final conclusion, and if this equation is satisfied, then the given x of t is called as the odd signal. So definitely this is an odd signal. But again, now I'll teach you by observation only how to get whether it is even signal or odd signal. Let us see. See, by observation you should understand whether it is odd signal or not. Whatever present at right hand side, on left hand side exactly minus of it is present. I mean, at right hand side if plus 1 is present, then on left hand side -1 would be present, and vice versa. That is, on right hand side if it is -1, then for odd signal on left hand side it has to be +1, and so on. In fact, what I always say to students, that there has to be always a symmetry with respect to origin, as you can see, or a diagonal symmetry. Diagonal symmetry means if whatever present over here diagonally opposite, there would be a same characteristic. In that case, it is always the odd signal. There is one more identity of odd signal, but that is not the only identity. That is one of the identity. First identity is to check every odd signal always has value equal to 0 at origin. Origin means at t equal to 0. You know that this is a signum function. At signum function, it is always 1 at t greater than 0. It is -1 at t less than 0. And by using the point of discontinuity, that is by using Gibbs phenomena, we know that at t equal to 0 we have average of both, which is 0. So this is the property of odd signal. Every odd signal has x of t value equal to 0 at t equal to 0, but not every signal which is 0 at t equal to 0 is the odd signal. As I said, it is one of the identity of odd signal. As you can see, even x2 of t, it is given over here, it is 0 here, right? But if it is 0 at t equal to 0, it is not that sufficient condition which will make this as odd signal. We will see more things. As you can see here, on right hand side we have positive half cycle, on left hand side we have negative half cycle. Is that right? Further, when I have negative half cycle here, then we have positive half cycle here. So as I said, on right hand side, if it is positive, on left hand side the respective thing in same shape, it has to be negative. In that case, that signal is said to be odd signal. And again, by having our common sense, this is actually sine theta signal, right? So this is sine theta signal, and we know that sine of minus theta is minus sine theta, or we say x of minus t is equal to minus of x of t. Then the given signal is said to be odd signal. So I'm sure now by observation you can identify continuous time signals if it is odd signal or not. Even this is applicable for discrete time signals also. So as you can see, x of n at n equal to 0 is 0. This is very important, right? And secondly, on right hand side if it is plus 1, on left hand side as you can see it is minus 1. On right hand side if it is plus 2, on left hand side it has to be minus 2. On right hand side if it is plus 3, on left hand side it has to be minus 3. With this symmetry only, the given signal is called as odd signal. So this is how you have to observe. So for odd signal, we have seen a common property, that is x of t is always 0 at t equal to 0, and even for discrete time signal, x of n is also 0 at n equal to 0. But as I said, this is not the sufficient condition. Sufficient condition is whatever present on right hand side exactly equal but opposite in polarity should be present on left hand side, and vice versa. If it is so, the given signal is said to be odd signal. Let us move ahead with the next classification, which is called as neither even nor odd. So these are some examples of neither even nor odd signals. Observe x of t. We will first of all check whether it is even signal or not. We know that whatever present at right hand side should be exactly present at left hand side, which is not. So definitely it is not even signal. Secondly, for odd signal we know that there has to be at least diagonal symmetry, right? There has to be compulsory, in fact, a diagonal symmetry. So there is no diagonal symmetry also, right? Secondly, this x of t is also not equal to 0 at t equal to 0. Therefore, if I say this is x of t, this is neither even nor odd signal category. Also, u of t signal is also neither even nor odd category, because whatever present at right hand side, nothing present on left hand side, right? I mean, not even diagonally. So if there is no diagonal symmetry, it is not odd signal. If there is no symmetry with respect to y-axis, that is whatever present on right hand side should be present at left hand side also, right? But since u of t is always 0 for t less than 0, this is also comes into same category, that is neither even nor odd. Even a ramp signal is also come in this category, that is neither even nor odd category, because as you can see r of t does exist only for t greater than 0. For t less than 0, it does not exist. It has got 0 characteristic here, right? So now we have to learn property of neither even nor odd signal. So it is a speciality of neither even nor odd signal. And what the speciality is, so we'll see what is a property of neither even nor odd signal. If x of t is neither even nor odd, so I'm assuming, let if x of t is neither even nor odd signal, in that case the given x of t signal can be expressed as summation of its even part and odd part. That is, it can be expressed as xe of t plus xo of t, where xe of t is called as even component. This is called as even component of x of t, and this is called as odd component of x of t. Only in which case? In case if the given x of t is neither even nor odd category, then definitely x of t will have two components hidden inside it, which is called as even component of x of t, denoted as xe of t, and odd component of x of t, which is denoted as x naught of t. Even this is valid for discrete time signal also. So our discussion is valid for continuous time signal here. For discrete time signal also, x of n, provided x of n is neither even nor odd category, it is equal to x e of n, that is even component of x of n plus odd component of x of n. If x of t happens to be neither even nor odd signal, then there is a formula in fact to calculate even component and odd component. So it is very easy to remember. See, if you want even component, that is x e of t, it is simply x of t plus x of minus t whole divided by 2. So what I'm doing, it is very simple. You just take x of t signal, add with time reversal of x of t, that is x of minus t, and then divide by 2. You get even component of x of t. For discrete time signal, formula is going to remain same. X e of n will be equal to x of n plus x of minus n by, very simple. Next, if you want odd component, you just do subtraction and whole formula remains same. Odd component of x of t is x of t minus of x of minus t whole divided by 2, and odd component of discrete time signal x of n is x of n minus of x of minus n whole divided by 2. So if you apply these formulas, then you will able to calculate even component and odd component of given x of t. Let us solve one problem based on this. So here is the question: calculate even and odd part of u of t. Let us begin. You know very well how u of t looks like. This is given signal u of t. We know that u of t is always 1 for t greater than 0, and it is equal to 0 for t less than 0. This is u of t. I'm sure you must have noted down the formula, so I'll directly write even part of u of t is what? It is x of t plus x of minus t by 2. So I can write this as u of t plus u of minus t whole divided by, is that right? So let us do this. We already have u of t. Let us plot u of minus t. So u of minus t is just a time reversal version of u of t. So now u of minus t is 1 at left hand side, and on right hand side it is 0. Yes, between these two signals we have to do summation. But as you can see, it is not just summation, it is also dividing by 2. And when you divide signal by 2, or let's say multiply by 2, then your amplitude gets affected, am I right? So let us do this. On right hand side this is 1, on right hand side this is 0. 1 plus 0 is 1, divided by 2 becomes half. So on right hand side we get exactly half. So on right hand side we have half amplitude from 0 to infinity. Let's talk about left hand side part. U of t plus u of minus t divided by 2. For u of t, on left hand side we have 0. On left hand side for u of minus t it is 1. 0 plus 1 is again 1. Again it is divided by 2. So it is half. So on left hand side, also on right hand side, it is half. So this is what we called as even part of u of t. Also, by characteristic it was quite clear. See, on right hand side, if already I had half, then naturally on left hand side I'll get same, because it is even signal, right? Because what we are ultimately going to calculate, even signal, and even signal has got that property, whatever present on right hand side, similar characteristic, in fact same characteristic should be present on left hand side also, right? So this is even part of u of t. Let us go on calculating odd part of u of t. We have the formula: odd part of u of t is u of t minus of u of minus t whole divided by 2. That is x of t minus of x of minus t whole divided by 2. First of all, let us have first component, which is u of t. This is what we call as u of t, which is 1 for t greater than 0. For t less than 0 it is 0. Then the second component is u of minus t. So u of minus t, it is time reversal version of u of t, which is 1 for t less than 0. For t greater than 0, it is 0. So what we are doing with these two signals, we are subtracting this, right? We are subtracting this. So let us perform subtraction. On right hand side, this is 1. On right hand side, this is 0. What is 1 minus 0? Of course, it is 1. But it is not just subtraction, it is also getting divided by 2. So 1 minus 0 divided by 2 is half. So on right hand side, what I'm getting is half. Am I right? Similarly, on left hand side, now this is 1. In fact, it is not 1, it is 0. What we have over here, we have 1. What is 0 minus 1? It is minus 1 divided by 2. It is minus 1 by 2. So on left hand side, we have minus 1 by 2. And in fact, if you remember, by common sense only, if we have half present at right hand side, definitely on left hand side, we will have minus half, because the resulting signal is odd part of u of t. And this is in fact property of every odd signal, that whatever present on the right hand side exactly equal but opposite in amplitude present at left hand side, or we have diagonal symmetry. Is that right? So don't you think it actually somehow looks like signum function? Of course, it could be a signum function if we had amplitude as 1 and minus 1. But instead of 1 and minus 1, we have amplitude as half and minus half. Therefore, this signal can be expressed in terms of signum function like this. It can be written as half signum of, so odd part is written as half signum of t. So as we said earlier, that if the given signal is neither even nor odd, of course, because the signal is neither even nor odd, then the given signal can be expressed as summation of even signal and odd signal. That is, if the given x of t is neither even nor odd, we know that we can write x of t as even component of x of t plus odd component of x of t. So tell me, in case of u of t, what is the even component? I can say even component is throughout half. So I can write half here, plus what is odd component of u of t? It is half signum of t. So I can write this as half signum of t. Is that right? And what is x of t? In our case, x of t is u of t. So this is the formula for u of t. So as you can see, u of t is expressed in terms of summation of two signals, that is even component of u of t plus odd component of u of t. So this would, I'll leave you as a homework. You try to add these two signals, that is, I'm talking about this even signal and odd signal. Just try to add these two signals and see to it whether you get same u of t signal or not. Okay, if you get, then your concept would be quite clear, that neither even nor odd signal can be expressed as even component plus odd component of the same signal. Thank you.